Right now, you are using the internet. You opened an app or a browser or clicked a link, and something happened instantly. A page loaded, a video buffered, a message sent. It felt like magic. It felt like wireless. It felt like it came from the air around you. It did not come from the air. What actually happened is stranger, older, and far more physical than you have been told. The internet is not a cloud. It is not a signal floating through space. The internet is a planet wrapped in cable, a web of machines buried underground and dropped to the bottom of the ocean, a system of invisible directories and silent middlemen that no one ever talks about. And right now, as you watch this, it is all running at once, perfectly, without you knowing a single thing about it. That is the secret internet beneath the internet. Let's go back to the beginning. Not the beginning of your device, the beginning of the physical thing. Imagine the year is 1858. Queen Victoria and President Buchanan are exchanging telegrams. Between them, several thousand miles of ocean. And at the bottom of that ocean, newly laid by a team of engineers who had no idea if it would even work, sits the first transatlantic cable. It is a copper wire wrapped in gutta percha, a natural rubber from Malaysian trees. It is fragile. It will fail after 22 days. But it works. For 22 days, two continents are connected by a thread at the bottom of the sea. That thread never went away. It just got upgraded. Today, there are more than 550 active submarine cable systems stretching over 1.4 million kilometers across every ocean on Earth. If you laid them all end to end, you could wrap them around the planet more than 35 times. These cables are not thick. Most of them are no wider than a garden hose. The ones in the deep ocean, miles below the surface, are actually thinner than your thumb, because down there is nothing to damage them. The heavy armored cables are only near the shore, where ship anchors and fishing trawlers can snag them. And these cables carry everything. Not some things, everything. 95% of all international internet traffic travels through submarine cables. Your email to someone in another country, the Netflix server in another continent pushing a video to your screen, a financial trade between Tokyo and London, a voice call from Mumbai to New York. All of it, right now, is moving through glass fibers at the bottom of the ocean, coated as pulses of light. Glass, not metal. The cables are not copper anymore. They are bundles of optical fiber, each strand thinner than a human hair, each one capable of carrying terabits of data per second using pulses of laser light. A single modern cable can carry more than 200 terabits per second. That is enough bandwidth to download every song ever recorded in about 3 seconds. But fiber optic light degrades. It weakens over distance. So every few hundred kilometers along the ocean floor, there is a small device called a repeater, a sealed underwater amplifier bolted to the cable, powered by electrical current running through the line itself, sitting in total darkness, in crushing pressure, in freezing cold, and silently boosting the light signal so it can keep going. Some of these repeaters have been sitting undisturbed on the ocean floor for over 20 years, with no maintenance, no replacement parts, no human anywhere near them. They just work. Now, think about what happens when a cable breaks. And they do break. Earthquakes shift the seafloor. Sharks, for reasons that still puzzle marine biologists, sometimes bite the cables. Anchors drag. In 2006, an earthquake off the coast of Taiwan severed 9 cables simultaneously, cutting internet access across most of Southeast Asia for weeks. In 2022, a volcanic eruption near Tonga destroyed the only submarine cable connecting the island nation to the rest of the world, leaving 100,000 people with almost no internet for 5 weeks. There are cable repair ships, fewer than 60 of them in the entire world, that can locate a break using precise electrical measurements, drag the broken end up from miles below the surface using grappling hooks, and splice in a new section. It is one of the most technically demanding engineering jobs on the planet, and almost nobody knows it exists.
So the data crosses the ocean. It reaches land. Now what? It arrives at a building, a very specific building. It is called a landing station, and from the outside, it looks like a bunker or a warehouse. Inside, it is climate-controlled, heavily secured, and filled with racks of routing equipment. The cable connects to a junction that hands your data off to the land-based internet infrastructure. From there, your data enters the terrestrial fiber network. Thousands of kilometers of underground fiber optic cables running beneath highways, railways, and cities, often following old railroad rights-of-way because those were the easiest routes to dig. In the United States, much of the fiber backbone follows the old railroad corridors of the 1800s. The infrastructure of the Industrial Revolution became the skeleton of the digital one.
And then the data reaches a data center. A data center is where the internet lives. Not metaphorically, physically. Every website you visit is a collection of files stored on a server. And that server is a physical machine sitting inside a physical room inside a physical building somewhere on Earth. When you visit a website, you are reaching out across the planet and pulling files off a specific machine. It is like going to a library, except the library is thousands of miles away, it answers in milliseconds, and you never have to return anything.
The largest data centers in the world are enormous. The Switch Data Center in Nevada covers over 700,000 square meters. The data center campus in Langfang, China is the largest in the world by some measures, spanning over 600,000 square meters. These buildings consume extraordinary amounts of power. A single large hyperscale data center can draw as much electricity as a small city, between 100 and 500 megawatts depending on scale. Where does that heat go? Because servers generate enormous heat. The answer is cooling infrastructure. Massive air handling systems, liquid cooling loops. In some cases, entire rivers or lakes used as heat sinks. Microsoft in 2020 ran an experimental data center submerged off the coast of Scotland, a pressurized cylinder resting on the ocean floor, cooled passively by the surrounding seawater, running on renewable energy piped from shore. It worked. It had lower failure rates than land-based data centers.
But data centers are not enough, because a single data center in one location cannot serve the whole world fast enough. The speed of light is fast, but it is not instant. The time it takes data to travel from one point to another is called latency. A signal from New York to London and back takes around 70 milliseconds just from the physical distance. For most uses, that is fine. For high-frequency stock trading, for real-time gaming, for video calls, 70 milliseconds is an eternity.
This is why the internet uses caching. A CDN, a content delivery network, is a system of servers distributed across the world that stores copies of popular content close to the people who request it. When you watch a YouTube video, you are almost certainly not pulling that video from Google's main data center. You are pulling it from a cache server that might be in your own city, maybe even inside your own ISP's network. That video was quietly preloaded onto that server because the CDN predicted it would be popular. Companies like Cloudflare, Akamai, and Amazon CloudFront operate tens of thousands of these edge servers around the world. Akamai alone serves between 15 and 30% of all global web traffic on any given day. The data is not coming from one place. It is coming from the nearest copy of the place. Now, here is where the internet gets truly strange. All of this, the submarine cables, the data centers, the CDN servers, all of it is useless without a way to address things. You cannot send a letter without an address. You cannot send data without one either. Every device connected to the internet has an IP address, a numerical label, a location identifier. When you type a web address into your browser, your device does not understand words like google.com. It understands numbers. So before anything else can happen, your device has to ask, what is the number for this name?
That question goes to the DNS. The domain name system is the internet's phone book. It is a distributed global database that maps every human-readable domain name to its corresponding IP address. When you type a URL, your device sends a query to a DNS resolver, usually operated by your internet service provider or by a company like Google or Cloudflare. The resolver checks its cache. If it already knows the answer, it returns it instantly. If not, it asks a root name server.
There are only 13 root name server addresses in the entire world. Not 13 physical machines, 13 addresses, each one operated by a different organization, spread across hundreds of physical servers globally using a technique called Anycast routing. The Internet Corporation for Assigned Names and Numbers, ICANN, coordinates this system. If the root servers failed simultaneously, the Internet's naming system would collapse. Websites would become unreachable, even if every cable and server in the world was working perfectly. This resolution process, from typing a URL to getting a response, takes on average between 20 and 120 milliseconds. You never see it. It is invisible. It happens behind every single thing you do online, billions of times per second, across the entire planet.
But where is the data actually stored? That brings us to the cloud. The cloud is a marketing word. That is the first thing you should know. The cloud is not a new category of technology. It is a new way of accessing old technology. When a company says your files are in the cloud, they mean your files are on someone else's computer, in a data center, somewhere on Earth. That computer is just very reliable, very fast, and not yours. What changed is the model. In the 1990s and 2000s, if you built a tech company, you had to buy your own servers, rent your own rack space in a data center, hire engineers to manage the hardware. It was slow and expensive. Then in 2006, Amazon Web Services launched. AWS was not originally a product Amazon intended to sell. It was infrastructure Amazon had built for itself, and then realized it could rent to others.
The idea was radical. Instead of owning hardware, you rent it by the hour. You need 10 servers for a product launch? Spin them up. You need 10,000 servers for a viral moment? Spin them up. You're done with the campaign? Shut them all off and stop paying. The infrastructure exists permanently at AWS. You just borrow a slice of it. Today, AWS holds somewhere around 31% of the global cloud computing market. Microsoft Azure holds around 25%. Google Cloud holds around 11%. These three companies together control the majority of the world's cloud infrastructure. Almost every major app, website, or digital service you use runs on hardware controlled by one of these three organizations.
Andrew Blum, a journalist who wrote the book Tubes in 2012, said something that reframed this entirely. He wrote that the internet is not everywhere. It is somewhere. It is in specific buildings, on specific streets, in specific cities. It has a physical presence on the planet. It has an address. And that address is not in the sky. The cloud metaphor was always a lie, a convenient fiction to stop you from asking where things actually are. But when you ask where the internet actually is, the answer is extraordinary. It is in a pressurized cylinder on the Scottish Ocean floor. It is in a garden hose-thick glass fiber coated in polyurethane, resting in the Mariana Trench. It is in a bunker in Nevada, drawing electricity from a solar farm in the desert. It is in 13 root server addresses that the entire naming system of the human internet depends on.
It is physical. It is fragile. It is an engineering miracle that mostly nobody thinks about. Right now, you are using the internet. And somewhere, a laser pulse no wider than a strand of your hair is racing through glass at the bottom of the ocean at 2/3 the speed of light, carrying this exact moment from a server to your screen. You called it magic. Now, you know what it actually is.